Good morning. Today I want to talk about a presentation I did last week on SoTiC, the symposium on thermoacoustics in combustion that was happening in Trondheim. So the title of my presentation is Output Only Identification via Generalized Polynomial Chaos. It's a topic I have been working with since already some years, and actually I want to apply to a thermoacoustic system. Okay, so let's go on. So in thermoacoustics, our interest most of the time is to understand the interplay between the flame response and the acoustic field. Well, each of these two subsystems can be understood by some parameters. For example, parameters theta ac or flow the flame response theta flame. And if we understand the model and the corresponding parameters, maybe we're able to understand the corresponding subsystems. Well, how do we do things most of the time? We use input output only or input output system identification to be able to infer those parameters from experiments or from numerical simulations. And we can use broadband forcing or harmonic forcing. But what is important is that the traditional method use input and output. For example, if we want to focus on a corresponding acoustic impedance, we can create a specialized rig and we just impose a proper acoustic wave. We measure the corresponding response and then we just apply some correlation methods to this input and output to be able to infer the corresponding acoustic impedance. For the flame, we can do something similar. We can send an acoustic wave, we measure the input perturbations of the flame, we measure also the global heat release rate, and we just try to infer some correlation to be able to obtain the gain and phase of the flame response or also the coefficients of the corresponding input response. So this is classical input-output system identification. So the question now is it possible to infer these parameters, theta ac or theta flame, with signals coming from experiments without external forcing? So this is actually the challenge I want to present you today. Well, now we do apply some modeling. So we have here the acoustic system that is characterized by the wave equation and the flame response, or let's say the flame that can be decomposed in the corresponding flame response influence and the source of combustion noise. Okay, so the question like this will be super ideal to be able to apply output only identification, but it's quite hard. So right now we have to simplify the corresponding problem. So what we do is we concentrate the information at hand around a solely or around a given frequency, which is most of the time the natural frequency of the system. So we can apply some bandpass filtering to really simplify the signal, let's say. We can apply some nonlinear models for the heat release rate with respect to a given input, and we end up with this equation, which is an ordinary differential equation on the amplitude eta. Okay? Now, maybe it should be understood better that there are several parameters characterizing the system. We have the damping, we have the flame gain, in this case the linear flame gain, we have some saturation coefficient, the eigenfrequency, and the noise. So here it becomes clear why we are talking about output only identification. Basically, the right hand side of the equation is noise, so the noise produced by the flame, which is actually the mechanism in which we impose force into the system, and because of that we will be able to infer the parameters of interest. Okay, so this is the objective: infer all these parameters only because the flame is excited or the system is excited by the flame itself. And there has been already some studies. So for example, Francesco Gani in 2022 already somehow put on the table this problem. He used maximum likelihood estimation to be able to infer the parameters, including the time delay, which was actually the most important. However, he realized that the whole procedure is challenging. So when you apply filtering to the signal, basically you affect the time delays estimation. And there are some work to do on the topic. Okay, so let me just present you like more classical methods that people researchers do to simplify even more the problem, to avoid tricks or let's say problems with the output only identification. So the first one, which is a bit, let's say, hard to understand at first glance, is neglecting the flame time delay. So basically say that the tau characterizing the time delay of the frame response is going to be 0. So in this case, the whole thing simplifies a lot, but you can already say, how is that possible? How does it make sense to just neglect the phase relation between the flame and the corresponding input? Well, actually, it makes sense if the damping effects stemming from the phase shift between P prime and Q prime are still accounted for in the system's damping alpha. And this is what happens. So when we infer alpha, we are not only inferring the acoustics, the damping of the acoustics by the system, but also the damping produced by this phase difference between the P prime and Q prime. Okay, but because of that, what was a tool for prediction now is, let's call it, just a tool for understanding, which is already super important, is very useful. But we have to say that with this assumption, we will not be able anymore to predict stability or new conditions of the system, because we are actually simplifying the whole analysis significantly. Okay, but now let's go on. And what happens when we apply this time delay equal to 0? Basically, what we're saying is that the corresponding derived equation is nothing but the van der Pol equation, which has been already studied in our community for some years. And we already see that there is a parameter nu that encompasses the influence of the flame gain and the damping of the system. We will call it linear growth rate. Okay, so it's interesting to see that even in this case of understanding, not prediction, but understanding is still super useful. You have an operating condition and the system is somehow unstable, and you are able from the signals to analyze the linear growth rate characterizing that system. You will be able to actually design passive control devices that will actually control that instability. And that's why one of the relevance of output only identification and the advantages of, for example, inferring this parameter nu. Okay, well, but this is not the end of the story. We need to simplify it a bit more, and we go from a second order differential equation to a first order differential equation. How? We use something called a slow time integration, and because of that, the equations is transformed. We are not talking anymore about the amplitude of the oscillation here, but of the envelope of the signal here in black. Okay, this is taken from a study of Nicolas Nore in 2017. So you can already see this transformation, but what is important here to highlight is that the parameters themselves, so nu, kappa, omega, they remain exactly the same. And this is what we want to highlight, because if we are able to infer some statistics or some quantities from the envelope, we will be able to gain quite a significant amount of information about the system. Okay, and of course, I'm not even close to be the first one to propose this. It was already proposed by Nicolas Nore and co-workers some years ago, already more than 10 years, in some seminar studies, as you can see here in this slide. Okay, and there are many methods to do what I just mentioned, to obtain these coefficients from the Langevin equation. Let me just remind you, this is the Langevin equation. So the equation that is characterized or describe the dynamics of this envelope A. Okay, so the methods mostly, or the most general one, consists in inferring the so-called Kramers-Moyal coefficients of an associated direct Fokker-Planck equation. This is quite tricky. It's already know that the calculation is far from trivial. So in order to improve the accuracy in the recent years, so also Nicolas and co-workers have introduced the adjoint Fokker-Planck equation. So this equation can be calculated multiple times and linked to the direct Fokker-Planck equation to be able be an optimization process to obtain the coefficients of interest. Okay, and because we have an optimization approach at hand, it's actually maybe less expensive if we first train a deep on it associated to this optimization problem, the adjoint Fokker-Planck equation, to be able to accelerate the whole identification process. And this was already introduced by Sugandhi, Dharmaputra, and Noire last year in 2024. Okay, so my introduction is now what I'm doing here. Well, I like identification, easy, and also I would like to propose a method that is simple and accurate. And the method that I want to somehow use is the so-called polynomial chaos expansion, or generalized polynomial chaos, actually the same thing, which is a well-established method for random processes. Here, for example, I give you an example of what is this about. Is basically describing a quantity which is random as a linear combination of defined random variables. So these here are polynomials on standardized random variables, and they are weighted by coefficients which are themselves deterministic coefficients. So if we are able to determine the deterministic coefficients of a given quantity, we'll be able to actually describe in a very precise way the randomness or the stochastic characteristics of this variable. Okay, so let's come back to our problem of interest. We have the Langevin equation, and the first thing we should do is to transform it into a forward Euler equation, so nothing fancy at all. And here, importantly, is that the A, B, and C, these are the coefficients of interest, are nothing but basically the linear growth rate, the saturation coefficient, and the noise intensity. Okay, so if we look at this equation, we realize that it is composed by a left-hand side and a right-hand side. The right-hand side has some input random variables. These are the ANs here. So the amplitude of the envelope at the step n. And we also have an input variable associated with white noise, which is the term that is going to force the system. Okay, this is a Markovian process, or this is simulated or studied as a Markovian process. So it means that what happens at an plus 1 is completely defined by what happens in the previous state, an. So that defines the entire process. So the first thing when we use a polynomial chaos expansion is to really be able to characterize these variables, the random variables, as a expansion. And in the first order approximation, so the first order expansion, this is the way we can understand things. Basically, the variable an is just the sum of the mean of the variable plus a standard deviation multiplied by a standardized random variable xi1. What is this xi1? Is nothing but a random variable which has a mean value equal to 0 and the standard deviation equal to 1. So you can already see that this somehow defines the randomness of an. Now we do the same thing for Zn, which is the noise. Also is characterized by a xi2. Importantly here is that by definition or by design, these two quantities are independent, are uncorrelated. They don't know anything about each other. Therefore, these two quantities should be also uncorrelated. Therefore, their inner product has to be 0. Well, now we go to the left-hand side and we say that the an plus 1 is also characterized by this polynomial chaos expansion. Here we have the mean value, and we have also some variability or some randomness, which is associated to the two variables chi21 and chi2. These two actually affects the statistics of an plus 1. And interestingly, but this is something in the paper, these k1, k2 are nothing but, or the sum and the square here is just the variance of an plus 1. Okay, if you read the paper, you will realize that at this point the expression is super long, super complicated, and you'll say, oh my god, what is this going on? But as long as we assume a stationary process, so basically we say that the mean value of an is equal to the mean value of an plus 1, which is here just written by mu, and the same for the variance, then we will actually completely simplify the problem to a very small system of equations. So, summarizing, we expand the equations that we just did, and then we project them. So this projection is not explained right now, but it's explained in the paper. And a given moment, so at the end of the problem, what we do is that the GPC coefficients can be, as I showed you also in the paper, are analytically obtained. But the nice thing is that these GPC coefficients, they can be also measured experimentally. So if you equate the measurements of the GPC coefficients with the corresponding analytical expression, then it's going to be possible to just solve the equations and obtain the coefficients of interest, which are actually A, B, and C. Okay, so again, growth rate, saturation coefficient, and the noise intensity. Okay, well, here we have the final system of equations that we need to solve. A 2 times 2 system of equations, everything is known from measurements, and we just need to solve for A and B. C is also obtained by solving this conditional variance that I will explain in a second. Okay, let's go now to the last part of the presentation. It's about how to explain or how to implement this. For the moment, it's going to be just synthetic data. And well, we do that like this. We just solve this equation, the Langevin equation, and we fix some quantities. For example, the saturation coefficient, we fix it to a certain value. The noise intensity, we fix it to a certain value, and we generate 13 cases for different values of the linear growth rate. Okay, all the values of A, B, and C will be used to solve the Langevin equation, and the whole idea is from the obtained signals to be able to recover the A, B, and C that we implemented at the first place. Okay, so these coefficients, all these things well obtained from the paper of Nicola in 2017. So how we can interpret this? Imagine we have we are in the case of growth rate 12. So this is a linear and so it's linearly unstable case. So it has reached a very large amplitude. So it is going to be oscillating like this quite a lot. And remember that we only track the envelope of the signal. That's why you can imagine that you are just capturing the envelope and it looks like this with this certain variability. And also you can somehow understand why when I decrease the growth rate, the signal amplitude is going to be each time smaller, and therefore the envelope is going to be at a lower level until I reach 0. In this case, we will have a neutral stable system, and then for negative growth rates, we have a stable system, and the envelope is going to be very close to 0. Okay, so we don't have really like these coherent fluctuations. It's going to be just mostly like noise, so the envelope of noise. Okay, so let's focus on this piece of signal, and we will just post-treat this signal, and we will see when we have the signal what we should do to actually infer the parameters A, B, and C. So the first thing we have to do is just to gather the amplitudes, so these A's, in a histogram. This is going to be called the marginal PDF, so probably of the corresponding AN here. And we will see that the mean value of this signal is going to be measured just by classical statistics, and the corresponding standard deviation as well. So we already see from this distribution how the mean value is around 5.4, let's say, and the standard deviation is somehow like 0.4, 0.5. So that's the first piece of information you can get from the signal. The second piece of information, at first hand, it seems more complicated, but it's not. So we want to construct something called the conditional PDF. So how we do with that? You just first have to just define an amplitude you want to study. For example, in this case, I define an amplitude to be mu plus sigma. So this is going to be an amplitude around here, you see. And the idea, I do the zoom here just to make things more clear, but it has to be also done in the entire signal. So if I just put this signal, the idea is to say, okay, now I will select with these red points all the regions of the signal where we have amplitude AN. You see here all the red points here. And the second step is I will just select the next point, and I will just depict it with this blue circle. And you will see that the next point sometimes goes down, sometimes remain in most of the same situation in the same place, or maybe can go upwards, so that there are some variability of this blue circle with respect to the red one, which is the previous one. Okay, so the whole idea is to gather all these blue circles and build a histogram, and this is gonna be called, actually, if well normalized, the conditional PDF. Okay, so the probability of AN plus 1 given that AN is equal to mu plus sigma. Okay, you will see that you can define other quantities, but this mu plus sigma for me was giving me good results. Okay, so the overall process is that it's just these two signals, these two PDFs. So you don't need to know anything about polynomial chaos expansion, because this is just to derive the equations. This is just basically mostly super fundamental statistics. So you get sigma, mu, and this variance of the conditional PDF, and that's it. So now let's go and solve the equations. So if we need mu and sigma, we can build this M matrix, which is a 2 times 2 matrix, and the vector here v1, v2 is also obtained from everything we know, and C can be actually obtained beforehand by this conditional PDF, like when obtaining the variance. So this is gonna be C, and sigma star is just some small calculation there. So basically, just solving this equation, you will get A and B, and remember that A is the linear growth rate and B is the saturation coefficient. C, as I mentioned, is already obtained from here. So now let's focus on these plots. I will show you just at the beginning for the case nu12. So this is the define. We want to find the true value. The true value we will know it beforehand, because this is how we design the signals. And now the idea is to recover it. So we will start. Something else is I do this thing not for one signal, but for 100 signals, because I want to be sure about the dispersion of how this AB, or the dispersion of the results of A and B. Because if the matrix M is ill-conditioned, small values of differences between mu and sigma will completely change the results of how the values of A and B. Okay, but I will show you also in the paper eventually that the condition of this matrix is actually not bad at all. Okay, so we start and we estimate the PDF of the GPC method, because we have calculated 100 times the same thing. And with very nice thing is that the dispersion of these PDFs, so the length of this is quite small. So basically the median of the whole PDF is just really very close to the true value, as you can see here, which means that the whole thing is actually quite robust for this particular case of nu equal to 12. Okay, now the whole idea is to compare with a reference method. So I will compare it here with the method of Norean-Schuermans, when you actually have to infer the Kramers-Moyal coefficients with some trick with the exponential extrapolation, and this is gonna be already quite tricky, as the authors over here also say in their papers that this method is quite sensitive and the dispersion is quite large. Okay, just to remind you, this is not the ultimate method, because as I told you, there is also the possibility of having an idemponet on the adjoint equation to make this whole inference process more accurate. But here I think it was fair to just compare something with the same complexity, or maybe similar complexities. And well, it's interesting to see that the method that I propose in this study actually well, is behaving better. Now we will just do the same exercise for all the coefficients. So here we have for the nu 10, nu 8, and we will see that the robustness of the method is maintained. So here the mean is a bit deviated from the truth, yeah, to be sincere. Here is also quite okay. And the dispersion of the reference method is, well, is getting worse and worse. And something interesting is for the stable cases here, the method actually somehow breaks down. So it has some extremely variability, and this is something that we have to work on later. And but mostly it's because the condition of the matrix worsens as the as the growth rate decreases. So the mu decreases, and somehow this becomes not as good conditioning as before. Okay, so that would be it. I would like to just have some highlights. The highlights is that the method is quite robust, and you just need to just solve a 2 times 2 linear system of equations. You don't need to know anything about polynomial causa expansion. So the polynomial causa expansion is just to obtain the final 2 times 2 system of equations. So as a practitioner, you just need to solve, obtain the marginal and the conditional PDFs, get some mu, some means, values, and standard deviations, and that's it. Okay. Now, this case, this whole method is very robust for unstable cases when nu is positive. For nu negative, we need to improve things, improve the conditional of the matrix. How? Maybe an idea is to increase the order of the expansion, because until now the polynomial causa expansion has been until the first order. Maybe we go to second order, things will be better. Okay, now something that we want to explore as well is to go beyond the Langevin equation. The Langevin equation was the first stage, but I think I'm quite positive that we can go to the actual Van der Pol equation, where the time delay is actually non-zero. So in that case, we come back to the predictability of the output only identification methods. So let's see. And finally, of course, is to make use of experimental data, because everything here was done with numerical data, synthetic data. So this is something we have to work on. Okay, so I hope you have found this interesting, and well, let's see what happens. Thank you very much.